Okay, so we're back. Okay. Yeah, no worries. So it looks like similar things across. Let me move the microphone a little bit closer. Okay, so I'm gonna tackle Lamonda's questions first, I guess. Oh, I need to connect this. Sorry. Hooray! Okay, we should be good now. Um, Let me just open this one up, and then we'll start with Lamonda's questions. Okay. Awesome. Okay, so let's see. So why is chloroform polar? We can talk about that. So if we take a look at what chloroform looks like, we have its Lewis structure here. Have some lone pairs. We can compare it with carbon tetrachloride. I think it'll be easier actually to look at carbon tetrachloride first, and then we can compare it with the other one. By the way, with this setup, like, is hearing okay and all that? Like, is there any problem with audio, echoey stuff? Just let me know. I keep switching things around, so I have no idea. Sometimes things get worse, sometimes they get better, so we'll see. Okay, audio is good today? Okay, that's good. Okay, so if we look at carbon tetrachloride first, um, we see this carbon is being pulled in all four directions at once. So it's being pulled from the top, from the side, from below, from, all sorts of different directions. And so we see that there's going to be no net um, movement of electrons. Sometimes it does seem like that, doesn't it? Okay, so if we look at this one, we have delta negatives across the bottom. We have a delta plus on carbon. However, we do not have anything pulling carbon from the top. So if you think all of these chlorines are kind of pulling on carbon a little bit, overall, that's going to end up pulling carbon's electrons like just downwards, if that kind of makes sense. So if you see that we have three kind of partial negatives all on the bottom, and we have no negative up top to cancel it out like we did with the other one. So as a result, it's just everything's gonna be pulled down. I can try and find a good picture of chloroform in its molecular shape. Okay, let's see. None of these are very good pictures, but let's see if we can see the chloroform dipole. These are really ugly pictures. Okay. Okay, here we go. This could kind of work. Okay. Let's flip open Google. Okay, so looking at this, drawing your attention to this spot here. Maybe I can make this bigger. No, it did not work. Okay. If you look at these are just basically carbon and chlorine with different amounts of hydrogen. So if we look here, like, we can see where the carbon is being pulled. So if we look at the far one on the right, that's carbon tetrachloride, we can see that we have carbon being pulled in all these different directions, and essentially all these little arrows are going to count. I'm not. Yeah. So Lamonda, we don't give H a partial charge because it's a non-polar bond. Okay. Yes. So I will make it simpler. Okay, compare these. Oh, I guess I have to show you back to the other one. Okay, we'll make it super simple. So I'm not even going to do 3D. So look at these structures that we have here. We can see carbon on the right structure is being pulled in all these directions. And if you think about it, the up and down are going to cancel each other out. The left and right are going to cancel each other out. So everything cancels out here. However, if we look at chloroform, carbon is being pulled to the left and the right equally, so those two will cancel out, but it's being pulled down, and we have nothing to pull it up. And so as a result, we're going to have a shift of electrons are going to be kind of more on the bottom half of the molecule. And so if you kind of like cut this molecule in half, we're going to see this, oh my gosh, this half of the molecule will be a little positive, and this half of the molecule will be a little negative, because there's nothing to cancel out. Okay, so imagine a tug of war, right? If you only have one person tugging on the rope, it's going to move, right? However, if you have two people tugging on the rope, one person pulling this way, the other person pulling this way, nothing's going to happen. And so that's essentially what we're looking at here. So the left and the right, they cancel out because they're being just pulled opposite. But the up and down, no one is pulling it up. So as a result, the electrons are going to kind of move down. And if the electrons are moving down, that means there's less electrons up top. And if we have less electrons up top, we are going to have a slight positive up there, and a slight positive on the bottom then. And so really this whole thing about symmetry is just trying to understand if these arrows will cancel out or not. So for a symmetrical molecule, they will always cancel out. And then for a non-symmetrical molecule, they're not going to cancel out. So that's why we're going to see that this will be polar and this will be non-polar. So I can maybe these two cancel out, and these four cancel out, but not there's nothing. I guess I shouldn't use an arrow. So we have nothing up top to pull. And so that's why it's going to be non-polar. Okay, cool. So let's pop open Discord, since I had to switch computers. Come on, Discord, you can do it. There you are. Okay, why would we use electron geometry over molecular geometry? Short answer, you wouldn't. However, we do need to know the electron geometry to begin with in order to find the molecular geometry. So right now we haven't had you really focus on bond angles, but you're going to see that, for example, we have two bent structures, right? We could have a bent that is we have two different bents, right? We have this one is going to be closer to 120 degrees. This one is going to be closer to 109.5 degrees. We're only going to know this by knowing that this one is electronically tetrahedral and this one is trigonoplanar. So it's not a common Maya, we should be okay on time. Her questions are pretty short. And other than that, it just looks like there's the three of you, so I think we'll be okay. I just don't want to forget any questions. So this is really the only time you would really consider electron geometry, is for bond angles. So These are technically both bent, but because they come from different electron geometries. I mean, more people are here for sure, but like question-wise, we only have 3 people asking questions. So that's why we would look at electron geometry. Okay, so question 3 is, are all molecules with 4 bonds and 0 lone pairs nonpolar? No, definitely not. Take a look at chloroform here. We have 4 bonds, no lone pairs. It is polar. However, if everything was the same, that rule would apply, but it is not a hard and fast rule. So 3, the answer is no. How do we know which mercury to use? Okay. This is how you'll know, because you will notice if you have this 2 here or not. Both of them have a 2 plus charge. The only thing different about mercury 1 is this little thingy here. So if you see that little 2, that's how you're going to know it's mercury 1. Mercury 2 does not have the subscript there. Okay, so hopefully that clarifies that bit. That's the only difference between those 2 ions. So you just have to notice if that subscript 2 is there or not. And number 5, no. It's just stuff from 4 and 5. And since that stuff is not really calculation heavy, we're not going to have like empirical formula and stuff like that. Okay, so you can dump that stuff from your brain until the final. And then panic, be like, why did I dump this from my brain? Okay, so Sherry has hung up on the term single bond. Okay, single bond. So, can you explain, Sherry, a little bit more? So if you're looking at that particular thing on the homework, it's having you kind of just do step by step. It's like the whole page is just one problem, and you're doing it step by step. So a single bond, like this is technically a single bond here. We also have single bonds all over the place. Like, all of these are single bonds. So a single bond is just one shared pair of electrons. And so it just tells you how many electrons are being shared. So a double bond is 2 pairs being shared. Yeah, so this one will have a double bond. So if you look on the structure you've drawn on the right, you have made it so that carbon is sharing 2 pairs of electrons with the oxygen, right? You're going to have to move a pair in, right? And so if you do that, you end up with this after you move that lone pair in, right? And so now this is called a double bond. And if you want to think about it in terms of electrons, it's exactly what you've drawn there on the question. You're sharing 2 pairs of electrons. Maya, can you rephrase that? I don't think I understand. You always include lone pairs for everything. So for like water, we definitely include the lone pairs, right? They will be important for us. Okay, so Sherry, I'm not quite sure exactly what you're asking either, Sherry. Would you be able to kind of go over this? No. Your answer should be the one on the right. Because if you look, the one on the left that you've drawn there, I'm going to try and duplicate it. From what I can see, it looks like we have I think this is what we have on the left there. So if we look at this, I don't think this has the right number of electrons either. I might not be seeing some because I it's in pencil. And my eyes are rotten. But let's go over how to do the structure. Actually, let's just do carbon dioxide again. Okay, carbon dioxide. So we have. No, don't worry. Yeah, so Lamonda is pointing out that this particular homework assignment is just, it's asking you to do step by step. So you kind of, we learn these as like, what, 5 or 6 steps or something. And so this particular homework assignment or that question is asking you to do one step at a time. And so it's kind of just saying that we know that the first step we do is we draw the single bond. That's our first thing. We draw our skeleton. And so we just have to kind of keep track of the electrons as we go. So for part B, you would not even put the lone pairs there. The skeleton does not have lone pairs because it's not complete. And so skeleton, this would be part B. You would just put this thing for part B. Okay, Maya, I see what you're saying. Okay, you meant for this particular question. Got it. Sorry for the confusion. You could draw a line as well. So remember, this thing is exactly the same as this thing. These are the same. Same as the lines. The lines are just a neater way of doing it. And so for part B here, you would just leave it as one of these two. Cool. And then you would go on and add on the rest of your electrons, make your double bonds later and all that fun stuff. Yeah, exactly. So we would finish the rest of it off later. You know, we would put our 6 electrons on each oxygen. We have none left. So we just check, okay, oxygens have 8 electrons. Carbon has 4. So poor carbon needs more electrons, so we would give it more. We could technically make a triple bond to one of the oxygens, but it's just typically better to do 2 double bonds. So we would move 2 pairs in, and we would make our double bonded one. And so we can see now that all of these have 8 electrons. And everybody is happy. Hooray! Okay, cool. So let's see. On number 4, how do you know this is a double bond? Okay, let me look up what number 4 is. Alright, let me log into Canvas real quick. 101. Oh, it's the same one. Oh, okay. Was it the same question then? Or... Oh, cool. Okay, well, okay, we just want to slow this one down. Okay, so you were looking more at like basically kind of part H, thereabouts. Okay. Okay, so then let me yeah, okay, cool. So let's go ahead and take a look at that again. So is getting to this part okay? Actually, let me just erase it all. Is getting to this level okay? To where we have the kind of okay, cool. So this part is okay, and so now it's just how do we go into the double bonds? Okay, so what we always want to do is we want to check each atom in our Lewis structure. We want to make sure that they all have the right number of electrons that they want. Excuse me. So the oxygens, they both have 8 electrons. Right, we can see we've got 2, 4, 6, 8 electrons on oxygen. Same thing on the other side. However, this carbon only has 4 electrons. And so we can just see how many electrons are kind of just around that carbon atom. And then, but we know that carbon, like most atoms, wants 8 electrons. And since we don't have any more to give, we had 0 electrons left to give out to our structure. This is when we're going to want to make a double bond. So whenever your central atom has too few electrons, we convert a lone pair on an outer atom into a double bond. So this is what's going to happen here. So technically we would do this step by step, but we can see it needs 4 more electrons. And since each bond is 2 electrons, we're going to need 2 more bonds. And so that's how that's going to work. And so from there, that's when we are going to now plop down some more electrons in there. Yeah, sometimes it helps to just have it in a sentence, for sure. And I'm happy to address that sort of thing. So let's have more questions. If anybody has any more, I'd be happy to address any questions or misconceptions. Oh. More questions, come on. Yeah, go ahead, Maya. Just post them in Discord and we can go over them. Yeah, but if anybody else has any, of course, go ahead, type them in there, and we'll have a look. You have me for another half hour. Might as well take use of it. Well, if no one else is asking, it's all yours. And you never know. I mean, they may have the same questions, so... Yeah, go ahead, type stuff up. While you do so, I'm going to plug in my laptop, because, yeah, streaming takes a lot of energy. So if you're on your computer, there should be a print screen button on your keyboard. Okay, you can try and write it. Yeah, that'd be okay. Well, maybe I could actually just find the part that you're talking about. I'll save this for now. We'll come back to it. Which lecture did you say it was? September. Maybe 29th? 29, okay. So let's have a look. Methanol. I thought you were saying SOS. Is like, I don't think there's, but I don't think it's that bad. Okay, yeah, go ahead. The ones on oxygen? So, okay, so our final Lewis structure should always include any lone pairs that we have. So that's actually what I thought you were asking before. So you see that anytime we have lone pairs left in the Lewis structure, we still keep them. Absolutely. It doesn't really make it easier, but it tells us about the shape of it, and we're gonna see if you take 111, that the number of lone pairs on it can have like charges. We're gonna see, but like in carbon dioxide here, we still keep the lone pairs on the oxygens. BF3, we keep the lone pairs on the fluorines. On the formaldehyde here, we keep the lone pairs on the oxygen. Always do it. Yeah. So anytime you have lone pairs left in your structure, you still have to keep them up there. So you're gonna find out in if you take 111 that the number of lone pairs will have and all other ones have lines. Okay, so I think I see what the problem is. So cool. Let's take a look at let's take a look at what's a good example. Let's look at this one. Okay. So I'm going to use a different color here. So in this particular example, when we first did it, actually, let me just go ahead and redo this whole one on today's notes. because that'll explain that, I believe. Okay, so we had selenium. We're going to color code this, and that's going to make stuff... Yeah. We can go over domains. So I'm going to color code this one first, and then we're going to see where those electrons are. So the total electrons was 6 plus 6 plus 6, which is 18. Remember, for our skeleton, we always put in one pair of electrons to each one, right? So for the green electrons, we have used 4 of them, right? Next step is to add lone pairs to the outer atoms, right? So we'll do that. So we have just used 12 electrons. We have 2 left. So we're going to add the last 2 to the central atom. Okay, so we kind of have our base structure shown. So as it is right now, it looks like we're going to need a double bond, right? Because selenium only has 6 electrons, and the oxygens have 8. So if it's all right with you, I'm just going to go ahead and erase one lone pair and now make our double bond. So hopefully that part's okay. We're going to see that these green electrons, those are shared electrons, or what are called bonding pairs. And so these ones become the lines. So when we redraw selenium dioxide, we're going to have our bonds are those green electrons. Why? Why what? Like, why are they lines? Where did I lose you? Making the double bond? Okay, so let's go back a step. Okay, so this is what it was before. If we look at our number of electrons on these, this oxygen here has 2, 4, 6, 8 electrons. The other oxygen, same thing, since it's the same. Yeah. So if we want to look at selenium now, selenium has 2, 4, 6 electrons only. And so selenium doesn't have enough. And so that's why we make the double bond. So we are going to then move a pair of electrons to make a double bond. So that's why we're moving them. Does that make sense? Okay. Okay, so I'm gonna just erase them and redraw them in the right spot. So all I did was we just moved those to make the double bond. So that now all of our atoms have 8 electrons. Okay, so um, so all the green ones that we see here, those are the shared electrons. Yeah. Okay. Cool. 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 And all these blue ones and the purple ones are going to be lone pairs. So we do redraw our lone pairs in our final structure. Oh my gosh, go away. I guess I'll keep these purple because I had them purple. So the purple and blue ones are lone pairs. And we keep those on our final structure. So we would keep them as they are drawn. So I will now, we can go over domains, and then I'll answer Lamonda's question. Okay, so domains. Okay, so. So electron domains are just things attached to the central atom. And so they could be one of two things. They could be an atom or a lone pair. Those are kind of the two options that we have for things that we could have stuck on our atom. So if we look at water, water has 4 things stuck onto it. There's the first thing, the second thing, third thing, fourth thing. So water has 4 electron domains. If we wanted to be specific, we would say that it has 2 atoms attached to it and 2 lone pairs. Or if we're kind of using our abbreviation, that's the same thing as writing AX2E2. 2 atoms, 2 lone pairs. So if we're counting electron domains, so this is one reason why it's important that we draw our lone pairs when we finish the structure, is that that's going to help determine its geometry. So if we're looking at this, we know that it has 4 electron domains. Anything that has 4 electron domains, so 4 electron domains means tetrahedral electron geometry. Every single time. Anytime you have 4 electron domains, your electron geometry is tetrahedral. Okay. Okay, yeah, sometimes it's hard to phrase exactly what you're trying to ask. Okay, so, well, I mean, we might as well just finish this one while we're on it. So we remember that our molecular shape will potentially change based on how many lone pairs we have. And if we go back to that lovely chart I drew, we find that if we have 4 domains with 2 lone pairs... Okay, yeah, that's fine, that's fine. All right. So as long as we can classify our molecule with the X's and E's, we'll be able to reference our chart and find that this one is bent. Ooh, Lamanda, I may have to have a look at that exam. So technically a bent angle for water is 104, but I think what I've taught you guys this semester is that it is just less than 109. So let me just take a look at the exam real quick. Which number were you looking at? Question 5, okay. Ooh, okay. Yeah. That particular semester I had taught these exact angles. For us, it's just going to be less than 109.5. So I would not worry about that particular question, Lamanda. That is from a different time when we taught more specific angles. So, yeah. It is interesting to see how... Yeah, exactly. So, yeah, thankfully for us, just understand that it is less than 109.5. Just a little bit. Honestly, if you put 109.5, that'd be fine too. I'd be okay with that. It just so happens that lone pairs push stuff a little bit stronger than atoms do. But that is not important for this level of chemistry. And yeah, it is unfortunate that the curriculum is always adapting, so it's like, people have decided, okay, we're not going to teach the specific angles anymore. It's like, okay. So, yeah, some of these things we might see, again, like if you notice something that makes absolutely no sense, chances are it's something that's not being taught anymore. And so, yeah. Let's take a look at any of these other ones on this. Okay, so I see why you were asking about percent mass and stuff, because I think at this particular point in whatever semester this was, we had covered that particular topic. So, again, yeah, it's just stuff that we've learned in the past 3 weeks. So, naming, electron configurations, Lewis structures. Yeah, lucky us. I probably do have another exam. Do I? I might have one, but it would not be multiple choice. But I guess it could be. I could just give you one. Just for practice, I suppose. Do you think that would help? Time to look at old Canvas stuff. Oops. Okay, I'll have a look. Let's see. How about from... So that was fall 18. Let's see what I did in... how about spring 2018? So this would be exam 2, right? Let's have a look. Does this cover the same topics? That's the real question. Kind of. So looks like there is still some stuff about... Actually, this would probably be okay. I could give this to you. Okay, I will upload these to Canvas for you guys, as well as the key. So again, this is not the format of this exam. Lavonda, is that from that exam as well, from the one in fall 2018? Okay. So for our class, again, this is due to a curriculum change. The real structure of phosphate is this. However, for our class, we are learning it like this. So this is the real structure. You'll learn that next semester, or if you take 111, you'll learn to do this way. But for us right now, we make it simple. We're going to have just this structure, and the structure as drawn on the right does not have resonance structures. However, the one on the left would, simply because the number of double bonds there. So that's another one. Don't worry about it, because that is a curriculum change thing. We have made it a little bit easier for you, not going into what's called expanded octet. Yeah, so unfortunately, it's like every time I write an exam, it's like, oh, no longer applicable. It's like, it's unfortunate. But 'tis what it is. Okay, so I have downloaded those. Let me upload them onto Canvas. Yeah, no. It's always good to, like, these are things you can always just post in Discord at 3 in the morning and, be like, hey, why does this answer key say 4 instead of 0? And I can answer that. Okay, so here are some more. Here's another set. Again, some of the stuff is gonna have like percentages and stuff, but that is not part of our exam for this time because we've already done that. Okay, so there they are. They're at the bottom there. So there you go. You can have a look at those. And yeah. I guess I should, let me take a look at the key for this one real quick. I put the key up, but let me take a look at it just to make sure there's nothing like that would. Okay, so for part, you'll see that phosphate is drawn there in the key. You can keep it as all the single bonds. I would not worry about that. Oh man, all the Lewis structures in here are more advanced. But it'll be okay. The way that you draw your Lewis structure for the selenate ion will still be tetrahedral, so you'll be okay. So yours will just have all single bonds, but the rest will be okay. Yeah, the rest, and then we have a bunch of naming, so we should be okay. Yeah, looks good. Okay, so there will be 2 parts on the key that you'll be like, what the heck? But just understand, just put single bonds instead of double bonds, you'll be fine. So that's something that you'll learn in 111 about formal charge and why we'll have to have extra double bonds. Okay. What? Okay. Anything else you'd like to go over? Yeah, no problem. So I'm just going to erase these just because I'm sure people will just get confused as heck over these. So we'll hide them. That never happened. Okay, so looks like I don't have any more to go over right now. But you guys are always welcome to post stuff in Discord if you want. And I can address those. So let me upload these. And look, it's not going to do it because it's going to be mad about the Wi-Fi. Okay, let's see if it posted. Not yet, but just watch. It's going to post twice as soon as I click this. Maybe. Okay. Well, in that case, I will see you on Tuesday. So Monday will be our exam. And then I'll see you on Tuesday for more. What are we doing next? Gases, maybe? I don't remember. Or maybe intermolecular forces. We'll find out. I have to look up what's on the schedule for us. Okay. See you guys on Tuesday.